Okay, shall we resume? Okay, so we break at this point. So I told you media trilemma. That means we have to optimize between three possibilities. Okay, so we want high SNR. So we need to make the grain smaller. But when you make grain smaller, you reduce the volume. So KUV by KBT becomes smaller. Then you end up having thermal stability issues, which prevent storing the information. Okay, so you can overcome this problem by increasing or choosing materials with high Ku. Okay, but problem is when you increase Ku, the anisotropy field is larger, which means you need more field to write information, but we have a limitation. So we don't have materials that can produce more than 1.5 Tesla like that for writing information. Okay, so we have some limit. So how we can move away from this problem? So the solution is always here. So we have to start from here. Suppose we solve writability problem, then we can choose materials with high Ku, and if we choose materials with high Ku, thermal stability is not a problem. You can make grain smaller. Okay, so solution always start from here. So one solution to overcome the writability problem associated with longitudinal recording technology is perpendicular recording technology. Okay, so in perpendicular recording technology, we can use media with a higher anisotropy constant. So thermal stability probability problem can be solved. Okay. Okay, so to tell you why perpendicular recording has a better writability, let's look at how we write information in longitudinal recording. So I told you longitudinal recording we use an electromagnet. So the electromagnet looks like this. So we have some coil. Okay, so we have some coil here. We send current. So there is a magnetic field. So the magnetic field will go between one pole to the other pole through the gap. Okay. Then the field also will go outside this region and go to the other pole. So this is very similar to the electric dipole concepts we have learned. So when you have two charges, the electric field can go straight and it will also go follow some curved path, right? So in a similar sense, the magnetic field from one pole to the other pole will follow many paths. So one is a straight path, another one is like this kind of path. So where do you think the field will be stronger? Where do you think the field will be weaker? Pardon? Away from the pole it will be weaker, but okay, so normally along this gap the field is stronger, and when you have fringing field is usually weaker. Okay. So here if you see the recording media is here, we are not using the strongest field to write information. So the strongest field is here, the gap, but we are using the weaker field, which is the fringing field for writing information. So, for example, if you get 1.5 Tesla or 2 Tesla here, you may get only like 0.8 Tesla or less than 1 Tesla here. So, we are using the weaker field to write information. So, that is why the longitudinal recording technology has a limitation. Okay. So, we cannot use this field, we call it gap field. So, the field between the two gaps is called gap field Hg. So, that is the strongest one, but we are not using that, we are using the weakest field to write information. So, there is no way we can use this field to write information in longitudinal recording technology. So, this is a problem. Okay, now, let us go and understand how we can write information on higher anisotropy media in perpendicular recording technology. So, there are two differences now when it comes to perpendicular recording. The head looks like this, okay. Instead of a ring shape, we have some other shape. Okay. So, here again we have a coil here. So, you send current through the coil in this region, you will produce magnetic flux lines. So, I have used the yellow color to show the magnetic flux lines that go through the blue region here. So, here I have a color code. So, all the blue region here are made using soft magnetic materials. So, whether it is longitudinal recording or perpendicular recording, the blue means there is a soft magnetic material. So, you know that when you send a current through the coil, the soft magnetic material can be easily reaching the saturation. Okay. So, it will produce more magnetic field. So, the blue color here is the soft magnetic material, and here again the blue color thing is the soft magnetic material, and we also have a soft magnetic material below the recording layer. So, the black one is the one that is going to store the information. So, we will store the bits here in this recording layer, but this one is a soft magnetic material. Okay. Now, let us say I energize this, I send current through the coil, I produce a magnetic flux. Okay. So, the magnetic flux will go from the head, go into the recording media, then it will pass through the soft magnetic material and return to the other pole. Okay. So, you can follow the path, right. So, there is a magnetic flux always follow a closed loop. Okay. So, it goes from one side to the other side. So, now we complete a loop. The recording layer is here, black is the recording layer. Now, what do you see? Do you see anything interesting? Okay. So, you can imagine that if this is the head and this is a mirror image. Okay. So, this is a mirror image of this. Okay. And if you look at this one, for example, let us say I rotate by 90 degree, I rotate this by 90 degree. So, now you see that this loop is very similar to this flux loop in the longitudinal recording, and the black layer is the recording layer, the black layer is in the gap. Okay. So, you see that we have virtually placed the recording medium in this gap. Okay. So, in perpendicular recording, this is the gap field, we are not using the fringing field anymore. This is like one gap, this is like another pole, one pole, another pole, and we are using this gap field to write information. Okay. So, it is a virtual gap. So, we are placing virtually in the pole gap. But when we do recording, actually the disk is like this, then the head is flying over. We are not like keeping the head, I mean disk in between the two poles, it is not possible. The head is so small, we are not doing that. Physically, we are not doing that, but we are virtually placing the recording layer in the pole gaps. because this is one pole, the other pole is here. Okay. So, this one pole, this is another pole. So, this is the gap field, and we are using this gap field to write information. Okay. So, this head is called a single pole head. Okay, I will come to that later. So, this is one of the earliest demonstrations of this kind of technique by Tohoku University in Japan. They came up with this perpendicular recording technology. So, in their initial demonstration, they actually placed the disc like this. So, they have a pole, single pole, this is the main pole, this is the return pole. They place the disc physically like that, but that is not practical, right. So, they finally came up with this design, where by using a soft magnetic material, you can create a mirror image of the head, and you can create virtual pole gap. Okay. So, now you can use this gap field to write information, and this kind of head is called single pole head. Single pole head, because you are using only one pole to write information. So, this is the pole that will write information. Okay, there is also flux lines here, the flux that comes through here writes the information, then there is a flux going back this way, right. Why this one does not write information or erase information? Pardon? Yeah, because these poles are big and the flux density is less. Okay. So, the magnetic field strength here will be very low. Okay. There is no writing happening here, even though there are two poles, only this pole is writing, because here the field lines are stronger. The flux lines have a large density. So, you have more field strength here and you have very low field strength. So, if you compare here, you may have like a 1.5 Tesla, and if you go this side, it may be 0.1 Tesla or something like that. Okay. Very low field, because this has a larger area. So, the flux lines spread over a large area. So, the intensity of magnetic field is not strong. So, you write using one pole. So, that is why the name single pole head. Okay. So, this was the very old demonstration in 1980s. Okay. So, now you know the objective, right. Now, the things are clear. So, you can produce a very large writing field, because we are using the gap field to write information. So, if you can generate high writing field, you can use materials with higher anisotropy constant. If your anisotropy is constant, you can make grains smaller. If grains are smaller, you can achieve larger SNR. Okay. So, that is how the perpendicular recording is advantageous. Okay. So, basically in the first demonstration, they placed the disc like this, and they showed that you can store information perpendicular direction. But what is the problem with this design? Let us say you have only one pole which generates perpendicular field, then you write on the disc by having another magnet at the bottom. What is the problem? Okay, there are two problems. Firstly, I told you that all the hard disk media has two surfaces. We write information on both surfaces. Okay. So, if you create something like this, you can write information on only one side. Okay. Whether if you write on the top surface, it will also write the same on the bottom surface. Secondly, if the disc has a thickness of 1 millimeter, then the distance between these two poles may be like 1.5 millimeter, and if you have 1.5 millimeter, the gap, the field will diverge, right. So, the field will not be focused, and if you have to focus the field, it will spread over large distance. So, you cannot write bits at high density. So, anyway, this is not practically useful, but this was the first technique they used to show the perpendicular recording technology. Okay, so, heads are nanometer sized and they fly at 1 nanometer high above the surface. So, the recording happens at the top 30 nanometer of the surface. Okay, so, whatever I have shown here, the head producing a field that going through the recording layer, coming back through the soft magnetic underlayer. So, all this is happening within a few nanometer layers. Okay, so, this is what happens. So, with this head you can record on both surface of the disc. So, here I am showing this whole thing happening in this small region. The head is much smaller than this. Okay, another advantage of the longitudinal recording and perpendicular recording technology is that longitudinal you are keeping the north or south like this to represent bit 1, right. But if you keep two north poles next to each other, what will happen? They will repel each other. So, when you go to very high density, the magnetization may tilt a bit away. The grains will not flip because grains are physically fixed, but the magnetization may slightly tilted. As a result, you cannot go to certain high density. Okay. On the other hand, if you pack perpendicular bits, so it is like north, south, something like that. This is very highly stable. So, because of all these reasons, the perpendicular recording technology is better than longitudinal recording, and in 2008 the perpendicular recording fully take over the longitudinal recording. Okay, so, let us do some questions. Okay, who is right, majority or minority? Minority. Okay. So, in longitudinal recording we are using the fringing field to write information. Okay, now majority is right. In perpendicular recording we are using the gap field for writing. I still do not understand why this person is wrong. Okay. So, all of the above is the correct answer. Perpendicular recording is better because of the single pole head, we have a higher writing field. I mean, single pole head plus soft underlayer enables us to get a higher writing field, and we can use high anisotropy media. So, all of the above is the correct answer. Okay, so in the old days, right, the longitudinal recording head looked like this. It looked like a ring, so people called it a ring head. But that is for longitudinal recording. For perpendicular recording, we are using a single pole head. Okay, next one. Oh, no clap question, but you can tell me what is the answer. So, even though we have two poles, okay, so we already discussed, because the field strength will be larger because of the smaller area. Okay, so here the area is very large, so the flux density will be very low, field strength is low. Okay, so with this idea, now we move on to the next topic. Okay, so now we move on to learn the details of a perpendicular recording medium, mostly focusing on the recording medium. Okay, so we just learned the media trilemma, and because of the writability issues, we have moved on from longitudinal recording to perpendicular recording. So, if you look at the layer configuration of perpendicular recording, you will have many layers, like these days I do not know, maybe more than 20 layers. Okay. So, we have some addition layer, soft underlayer, seed layer and so on. Okay. There will be so many layers. So, for the next 1 hour I will explain to you why we need so many layers, what is the function, how these layers help and so on. Okay. So, to deposit all this, I told you the production system has many stations. So, the sample go from one station to the other station. So, in the modern deposition tools may have about 24 chambers or even more, okay, because when you have 24 layers, you need sometimes more than 24 chambers, because sometimes you may have to cool the sample or heat the sample. So, you need a heating station, all those things. Okay. So, usually the chambers will be much more than the number of layers you see here. Okay. So, like with what we learned for longitudinal recording, even if you design a perpendicular recording, you need to find ways to reduce the background noise, you need to find ways to reduce the transition noise and so on. In addition, okay, so if you want to reduce the DC noise, you want to improve the crystallographic orientation. So, I told you in the case of longitudinal recording, you want to make the magnetization in plane. So, to achieve that, we grow some underlayer we learned, right. So, the underlayer helps to keep the easy axis in plane. So, similarly, in the case of perpendicular recording, we want to have the easy axis perpendicular. So, we do not want deviation like this. Okay. So, we want to make the easy axis to be as perpendicular as possible. So, we not at all, we are not at all interested in this. Okay. So, we want to maximize the C axis of all the grains to be perpendicular to the direction. Okay, so that is how we reduce the DC noise. So, we need improved crystallographic orientation. We do not want too much gap between the grains and so on. Okay, so, similarly, like we did with the longitudinal recording, we want to reduce the transmission noise. So, we have to isolate the grains from each other, and we want to make grains as small as possible and so on. So, all this knowledge that we learned are still applicable. But in addition, now you have another problem. So, previously longitudinal media you have only one magnetic layer, so only one source of noise, but in perpendicular recording media you have another magnetic layer. So, if you remember, there was a soft magnetic layer below the recording layer. So, that will also be a source of noise, that will generate some magnetic field. So, there will be some noise coming from this soft underlayer, and this also have to be solved. So, this problem is unique to perpendicular recording. This problem did not exist in longitudinal recording, but this was a new problem, and it was a headache for many years. So, people took long time to solve this problem, but finally they managed. Okay, so, if you look at the functional aspects of perpendicular recording layer, we can say that there are 4 layers. For example, the soft magnetic underlayer is part of the writing process. So, your head is here, from the head, I mean from the height, the head is producing a magnetic field that goes through the soft magnetic material and goes back. Okay. So, this is part of the writing operation, and you have the intermediate layers to achieve the C axis orientation. So, that is one thing. Secondly, like you have 2 magnetic layers, and if you let them couple with each other, then you are going to lose the properties. Okay. For example, the coercivity of the recording layer so coercivity of the recording layer is around 6000 Oersted, let us say, and coercivity of the soft magnetic underlayer we usually use SUL, maybe 1 Oersted. Okay. So, if you put the 2 layers together, the soft layer will become hard, the recording layer will become soft. Okay. So, you are going to spoil both of them. Okay. So, it is like having a saint and thief together. Okay. So, they are going to spoil each other. Okay. So, you do not want that. So, you separate them using intermediate layer, that is another reason. Okay. So, you want intermediate layer for 2 purposes. One is to make the C axis perpendicular, this is one purpose. Second purpose is to separate them so that they do not interact, and hard layer remains hard, soft layer remains soft. If you do not have this layer, then hard layer will be a bit softer, soft layer will be harder, it is not good. Okay. So, you have this intermediate layer. and you have the overcoat lubricant for corrosion protection and the mechanical property improvement and so on. Okay. So, this is a very simple picture of the functions of different layers, but once you get into the detail there will be many more layers. So, right now I show you only 3 layers, but 3 layers are not good enough to achieve high performance. You need to keep improving them. Yes. So, why this is 20 to 14 nanometer, why this is 15 to 30 nanometer? Okay, there are 2 ways to look at it. One way to look at it is, let us say you achieve the desired properties at this thickness, then will you choose 100 nanometer? No, right. So, you if you can achieve the desired properties within this thickness, you do not go for higher thickness. Okay. Why we do not go below this thickness is because we cannot achieve the desired properties. So, the objective of this soft magnetic underlayer is to collect the magnetic field from the head. So, it will receive the magnetic field, send it back to the head, right. So, if the thickness is below this, then there will not be enough magnetic field lines going through the soft underlayer back. Okay. So, writing will not be good. So, writing is not good, and if thickness is above 40 nanometer, then you will have the noise issues which I just showed you before. Okay. The noise will be higher, and moreover you do not want, you need to make the sample sit in the sputtering chamber for longer time, you need to deposit thicker film is unnecessary. You are spending more time, more money is not necessary. Okay. So, there is a optimum thickness. So, similarly same thing here. So, if you make this intermediate layers thinner than certain thickness, then you cannot make the C axis of the cobalt perpendicular. So, there is a lower limit. If you make this thickness very large, then what you are doing is that your head is far away from the soft underlayer. Okay. So, you want to make the soft magnetic underlayer as close as possible to the writing head. Writing head is somewhere here. So, it is producing a magnetic field and it will diverge, right. If you have a magnet and if you go away from the magnetic field is going to diverge. Okay. So, you do not want to go here, the magnetic field is going to be weaker, you want to stay closer to the magnetic poles. Okay. So, we do not want to make this very thick, in that case this layer is far away from the head. Okay. So, there is some reason why we choose different thicknesses. Okay. So, now in a very simple level we have 3 layers. Now, let us go on to the detail. So, I said one soft magnetic underlayer, but the soft magnetic underlayer is not one, at least there are 3 layers. So, you see one here, another blue layer, then there is another layer, there are 3 layers, and even the soft magnetic material you cannot directly deposit on substrate, we need some layer to improve the addition. So, we are depositing many layers, right. So, these layers, all these layers should not peel off from the disc. So, we need to improve the addition. So, people usually deposit some layer like titanium, alloy or tantalum. So, these layers stick very well to the substrate and all the other layers also stick very well to the substrate, this layer. So, this is like a glue. Okay. You can imagine This is like a thin film glue. Okay, so we have some glue layer, then softened layer is already 3. Then we have seed layer, ruthenium 1, ruthenium 2 and so on. So, these are equivalent to the chromium layer that you learned before. Okay. So, these 3 layers that I show here help to achieve the C axis of cobalt in the perpendicular direction. The ruthenium 1 and 2, the element is same, but there is some difference which I will show later. Seed layer is a nickel tungsten alloy. So, it is an alloy of nickel and tungsten. So, when I taught you about this chromium, right? So, I told you that this chromium will have certain crystallographic nature, but that if you want to improve the crystallographic texture of chromium, it is better to have some other layer. Okay. So, in this case we have ruthenium layer. So, this ruthenium layer has a hexagonal structure. So, you have to make the C axis of ruthenium to grow in this way, then you can grow cobalt on top. Okay, so, the ruthenium is the bottom Lego block. Okay, so, we will go into the detail. Time being, just notice that there are so many layers for certain purpose. Okay, so, I will not go through the details of softened layer. Yeah, let us skip this one, but anyway you join the booklet. Okay, so, let us do the vocab questions. First question is this. So, you have magnets arranged in certain fashion. You can imagine that blue is north and red is south, something like that. Sorry, just hold on. Okay, so, you all need to join again, sorry for that. Please join again. Okay, so let's do question 1. Okay, so we learned during the longitudinal magnetic recording that if you have two like poles pointing each other, there will be a strong out of plane magnetic field. So, in this case B will generate a large magnetic field, C also will generate a large out of plane magnetic field. So, the one that would generate the least magnetic plane field out of the plane is A. So, majority of you are right, again 2 is wrong. I do not know, this 2 is a magic number. Okay, next question. Okay, who is right, majority or minority? No, least, right? Least is A, majority is right. So, I told you that the signal that comes out of the recording media is proportional to MRT, right. So, if thickness is large, you will have more magnetic flux. Okay. So, B will produce more magnetic flux and A will produce less magnetic flux. Okay. So, this brings us to the point of soft underlayer noise and also to the question that you asked, right. You asked why the thickness cannot be large. So, if thickness is large, you are going to generate more magnetic field out of the soft underlayer. Okay. Let us say this is how the disc looks like and you have deposited a certain soft magnetic underlayer. The soft magnetic underlayer is a normal thin film, so it will form multi domains. Okay. So, let us say it forms domains like this. Okay. So, there are some domain with magnetization in this direction, some like this and so on. Okay. So, there will be some head to head domain, and if you look at this region, this is like the longitudinal magnetic recorded bits, right. So, there will be some stray magnetic field that will come out of the soft magnetic underlayer. So, if the soft underlayer is too thick means there is more magnetic field. So, that is noise. So, we do not want that, and we do not even want any domains like this. Okay. So, this was a problem for long time. Then finally, people solved this problem by having two approaches. One approach is to have some kind of radial anisotropy. Okay. They during the deposition, we know the magnetron sputtering, right? Magnetron sputtering, there is a magnetic field. So, that magnetic field can be designed in such a way that you can induce an anisotropy along the radial direction. Okay. So, if you somehow make the soft magnetic underlayers anisotropy to point along the radial direction, there will be no such domains. Okay. Then there is no noise. So, this one approach. So, this they solved by the design of the magnetron. So, by designing the magnetron, they produce a stray magnetic field. That stray magnetic field orients the produces a field induced anisotropy along the radial direction. So, this was one approach. Okay, so, this is what is called radial anisotropy. It is by the type of the magnetron design. Okay, so, we design the magnetrons in such a way that when you place the disc. So, this is a disc, I do not know if you can see clearly, there is a disc held by someone's hand, I do not know my hand or someone else. Okay, there is a disc and there is a magnetic field. So, that magnetic field forces the easy axis of the soft underlayer to point along the radial direction. So, this is one way we solved, and not keep, I mean during the deposition that field is always on. So, you have a substrate and you have magnetron is rotating, even though the magnetron is rotating, this component is always in certain direction that the radial anisotropy exists. The field lines, okay, when you see this white, right, when you see this white, it basically means the magnetic field is going from this to this. Okay. So, the magnetic field is always in the radial direction, that forces that induces a magnetic anisotropy along the radial direction. This picture is like we open the chamber and we place a sheet above the magnetron, then we can visualize. So, there is a, I mean you can buy this kind of sheet in Amazon. So, it's magnetic visualization sheet. So, if there is a magnetic field, you put this sheet, you can visualize. So, the field lines are like this. So, this is based on the heart shaped the magnet array which I showed you on day 1. Okay, so, this one approach we can solve the problem. Then another approach, maybe I will not go through this in detail because this needs more discussion, is basically splitting the soft underlayer into 2 layers and by inserting a thin ruthenium layer in between. So, if you do that, the magnetization of the 2 layers will point in opposite direction. So, this is another way. So, we call this synthetic antiferromagnetism or antiferromagnetically called soft antiferromagnetically coupled soft underlayer. So, this was another approach through which people reduced the noise. For example, you just deposit the soft underlayer and you fly the reading head over the soft underlayer. So, this is the left side is a single soft magnetic underlayer. So, you will see that there is so much signal, right. So, it is not low, it is very high, some region you have red, some region you have blue and so on. So, these are regions where you have domains and there are stray magnetic field. So, this is noise. On the other hand, if you make this AFC soft underlayer, basically you break the soft underlayer into 3 layers like I show here. Okay, so, here you see 3 layers, right. So, this 3 layer design is called antiferromagnetically coupled soft underlayer. There you see the noise is very low, it is like the blue range means the noise is very low. Okay. So, this was one way to solve the problem. Okay. So, now you understand why soft under layer is not a single layer, but 3 layers. Okay. Let us skip this question, let us move on. So, if you want to know what are the materials used in the soft under layer, typically they are some alloys of cobalt. So, you add a tantalum, zirconium to cobalt, then you get a soft magnetic material. Okay. So, the 3 layer structure is like one soft under layer, one thin ruthenium, then another soft under layer. Okay. So, now we are going from the substrate, then you have addition layer, 3 soft under layer, this is already 4. Now, we will go on to learn more layers. Okay. Now, we discussed the DC noise before, then we learned that we want to maximize the grains with the perpendicular z axis. Okay. Let us do some question. This time not 2, 5. Okay. Okay. So, configuration C will give the DC erase noise, right. To minimize the DC erase noise, we want to make all the grains to have perpendicular EZ direction. So, A is preferred, B is less preferred, C is the least preferred. Okay, next question. Now, is magnetization direction. Previously, it was EZ axis direction, now is magnetization direction. Okay, so, when you erase media, you want all the magnetization to be perpendicular. So, A is the most preferred, B is less preferred, C is the least preferred. Okay, so, C is the correct answer. So, in longitudinal recording, we want to be perfectly parallel, right. That is the one which gives the least DC noise. Here we want them to be completely perpendicular. So, A is the best one. So, see what happens, one grain has flipped, one magnetization has flipped. Okay, so, let me draw. if you have all magnetization pointing like this, right, and if you fly the head over this disk media, you will have some constant voltage. Okay. So, this is better. Right. On the other hand, if one is flipped like this, then you measure the voltage something like this. So, if there are many flip, then you will have something like this. So, this is not perfect. Okay, so, let me skip all these things. So, in the case of perpendicular recording, we want to make all the grains to point in the perpendicular direction. EZ axis has to be perfectly oriented, that is what gives rise to a low DC noise. If the EZ axis has random magnetization, that is not good. If there is lot of space between the grains, that is also not good. So, when there is lot of space, then again when you fly the head through, then you will have like this. Okay, there will be noise which you do not want. And if some grains flip their magnetization, that also will give rise to a large noise. So, we do not want this. So, we want to make all the grains to have perpendicular EZ axis direction. So, for that purpose, we need intermediate layer. So, I told you before already that we use the intermediate layers to achieve the C axis orientation perpendicular. So, in longitudinal recording, we use chromium to have in plane magnetization. In perpendicular recording, we use ruthenium to get the C axis perpendicular direction. Okay. So, if somehow if you make the ruthenium to grow like this with the C axis perpendicular like I show here, then cobalt has a very similar lattice structure. So, the cobalt atom can grow on ruthenium like Lego blocks, it can grow with the EZ axis out of plane direction. Okay, so, that is the reason why we have ruthenium layers, and basically this seed layer here I showed tantalum, in the other slide I showed you nickel tungsten. Tantalum was very old technology like 20 years ago, nickel tungsten is a later technology. So, by having this seed layer, you can maximize the ruthenium grains which have C axis orientation perpendicular. Okay. So, if you choose a proper seed layer, the number of ruthenium grains with a C axis perpendicular will be increased. So, if that is the case, the number of cobalt grains with the EZ axis in the perpendicular direction will also be increased. Okay, so, that is one reason why we have ruthenium layers. Okay, is it clear? Okay, so, another reason I told you is okay. So, you can check this property by doing XRD. So, if you grow ruthenium and you grow cobalt on top, you will see ruthenium 002 peaks, cobalt 002 peaks. So, by doing XRD, you can understand this ruthenium growth. Okay, so, let us do some questions again. And the second reason I already told before, right? You have a soft layer, hard layer, you want to decouple the two layers. Okay. Okay, all of the above is the correct answer. Now 2 has become 3. Okay, so we are using ruthenium layer to improve the crystallographic texture and also to prevent the interaction of soft underlayer and the recording layer, two purpose. Okay, again magic number. Okay, so we use ruthenium layer to help improve the C axis, seed layer to improve the C axis orientation of the ruthenium layer. Okay. Okay, so the science of why on certain layers the ruthenium gets better C axis orientation is not clear. Okay. So, for example, the early days people used tantalum as the seed layer, then people grow ruthenium on top of tantalum. So, in this case let us say 90% of the ruthenium grains have C axis orientation perpendicular. So, 10% let us say they are slightly off. Okay. Then later people found that if you use nickel tungsten and grow ruthenium on top, then maybe you can improve this percentage to 95%. Okay. I am just giving you some number, these numbers are not very accurate, but I am just giving you some idea. Okay. So, if you change this layer from this to this, you get improvement. Okay. So, we do not know the science, why it works, we do not know, but in the industry there will be at least one scientist to look at this issue. Okay. So, imagine one scientist to just focus on one layer. Okay. So, by tuning the properties, we keep improving from 90 to 95 to 96 percentage and so on. Okay. And developing theory will take very long time and no one has time. Doing experiment is easy. So, they just experiment with various layers to improve the C axis structure. Okay, now let us move on to the other point. We learned yesterday that we want to keep the grains separate from each other, so that when you switch this grain, you do not switch the other grain. Okay. So, we want to make the grain separated from each other. So, for that purpose, yesterday I teach you the concept of compositional segregation. That is one way to make the two grains separate. So, in compositional segregation, you have two grains which are magnetic and you had non-magnetic boundary. So, in perpendicular recording also we can do, but we can also employ another technique based on something called Thornton diagram. Okay. So, this scientist I think 50 years ago he came up with this diagram. He deposited various films at temperatures ranging from closer to melting point and low temperature and at various pressures, and he found out that let us say your temperature is low somewhere here, and if your pressure is high, then your films will grow like columns separated from each other. Okay. So, if you use high pressure and if you grow films at room temperature, for example, okay, not you are not going to very high temperature, you grow at a room temperature, then you can grow films like this. For example, if you take ruthenium and if you grow ruthenium at high pressure, then you will have ruthenium grains which will look like this. Then this region will be void. Void means nothing in between, so empty space. So you can grow films like this. Okay. So in industry, we also employ that technique. So you look at the transmission electron microscope image of two ruthenium layers. So there is one ruthenium layer grown at 0.5 Pascal of sputtering pressure, and another ruthenium was grown at 8 Pascal. Okay. So here the ruthenium grains are continuous. You cannot see any grain boundary, but here you see there are some white regions, right. So these are all spaces, empty space. So when you grow ruthenium at high pressure, you grow them like this. So the rutheniums are separated from each other. So there is some empty space. Okay, so this is one concept we employ. So Rajan, you asked why we have two ruthenium layers, right? So in the perpendicular recording, we use two ruthenium layers. One of them is sputtered at high pressure. The one at the top is sputtered at high pressure. The other one is sputtered at low pressure. Okay. So why we need to? Why not just this, or why not just this? Is because we need this to separate the cobalt grains from each other, because this gives rise to low transition noise. So we need high pressure ruthenium. But why not this alone? Why we need low pressure? Is because if you try to grow high pressure ruthenium on top of some seed layer, the C axis alignment will be random. Okay. So you need low pressure ruthenium for better C axis texture, and you need ruthenium to get this grain separation. Okay. So in one word you can say we need ruthenium, one layer for reducing DC noise, the other layer for reducing the transmission noise. Okay. So this is why we have more ruthenium layers. Okay, which I have summarized here. So we have layer 1 for improving the C axis growth, layer 2 to obtain a segregated grain structure. Okay, so cross section will look like this. So ruthenium 1 will be flat, and ruthenium 2 will be having segregated grains. So this is what I was showing. So if you grow ruthenium films at high pressure, you see the C axis is not very good. The intensity, peak intensity gets reduced, right. So you cannot just use one layer. Okay, so now we move on to the next concept. We learnt about the softened layer, we have learnt about intermediate layer, now we are moving to the recording layer. Mm-hmm. Yeah, it is helping. I mean, the ruthenium is helping or enhancing. Without the high pressure ruthenium, the separation is not that good. Yeah. So yeah. So okay. Now we go on to describe the recording layer. So yesterday we learned the compositional segregation. So I told that tantalum helps to make the grain separate from each other through some non-magnetic grain boundary. Then this morning I showed you that boron was better than tantalum, but in perpendicular recording we use some form of oxide to separate the magnetic grains. Okay. So, here what you see in the grain boundary is a region rich in oxygen. Okay, so, you have cobalt rich grains, then you have oxygen rich grain boundary. Okay, so similar to what we discussed yesterday. So, you have a magnetic grain and a non-magnetic grain boundary. So, which makes all these grains to be single domain grains. So, they switch by Stoner-Wolff or reversal mechanism. So, thereby we can reduce the transition noise. Okay. But one difference is yesterday when we discussed, we need a temperature of around 250 degree to achieve this compositional segregation. But in the case of perpendicular recording media, we can achieve this oxide grain boundary even at room temperature. So, only thing we do here is we deposit this layer also at a high pressure. So, instead of 1 Pascal or below, we may sputter this oxide target at around 7 Pascal, 5 Pascal at high pressure. So, during the high pressure we have different mobility, lower mobility for the atoms. So, they segregate like this. Okay, so, if you ask what are the elements inside perpendicular media, so typically it is a cobalt, chromium, platinum alloy, and chromium is very little, around 7 atomic percentage, mainly for the corrosion properties. So, you want to reduce the corrosion properties of cobalt. So, you have some amount of chromium. Platinum could be around 18 atomic percentage, then some form of oxide. So, these days we have more than one oxide. So, you may have a mixture of silicon oxide, tantalum oxide, something like this. So, let us say 4 atomic percentage. So, 4, 4, 8, 26, 33. 16, 26, 33, 40. So, something like this. Okay. The composition will look something like this. Okay. So, again like I said, in industry there will be one engineer for one seed layer. Okay. So, there will be a few engineers to look at this composition, how we can make the grains better, how we can improve the properties and so on. Okay, so, the platinum helps to improve the anisotropy. So, if you want to increase the Ku of the material, you increase the platinum concentration. So, if you start with say platinum 14, low anisotropy, if you move to platinum 18, there will be high anisotropy and so on. But there is a limit, you cannot like keep on increasing platinum and keep on increasing the anisotropy, there is some limit. Okay, by playing with the platinum concentration, we improve anisotropy. By playing with these additive elements, we segregate the grains, and chromium we use a bit for corrosion properties. Okay, so let me skip some of this. The oxide does not stay as oxide. I mean, your target will have oxide, but when you do sputtering, I mean, you are not maintaining this oxide. What you have is like this oxygen goes into the grain boundary. So, your grain boundary is oxygen rich. the grains do not have oxygen. So, you have magnetic region and non-magnetic region. Okay, so now we have learnt many layers, right. So, we have learnt about addition layer, 3 seed layers, sorry, 3 softened layers, then seed layer we have ruthenium 1, ruthenium 2 we have learnt about magnetic layer. Again this magnetic layer is not going to be one, it is going to be many. Okay. So, for that again we come back to the writability. So, I told you that the writability is the one that limits how high density we can go. So, we have to find out some ways to improve the writability. Okay. So far I have been discussing that the magnetic recording grains that we have in the recorder media, they should switch by Stoner-Wohlforth reversal mechanism. Okay. In this case, the anisotropy field of your material is proportional to 2 Ku and inversely proportional to m, and this is what will limit the field. Okay. So, your field, the field you apply has to be larger than Hk, only then you can switch the magnetization. Okay. So, as I told you before, the maximum Bs that we know of materials is around 2.5 Tesla, but when you make head you will get something like 1.5 Tesla. So, Hk cannot be more than 1.5 Tesla. So, there is a limit. Okay. So, if you want to switch further, we have to move away from this. Okay. We have to go away from coherent switching to something called incoherent switching. Okay. So, there have been many ideas floated around to achieve this incoherent switching. Okay. So, I will not go through all the details, but I will give you a very simple explanation. For example, let us say you have 2 layers, hard and soft. Soft means not exactly like a softened layer. For example, you may have a one layer where the Hk is 10 kilovolt, another layer with a slightly softer property with Hk of 66 kilovolt. Okay. So, this kind of structure is called exchange coupled composite media or exchange spring media. There are many names, there are many formation of this kind of, basically they all rely on using some structure like this. Okay. So, you can easily understand this one by some analogy that I am going to give. Okay. So, you can make it like soft hard, or you can make it like soft hard going gradually from softer to harder, things like that, or you can break this into many, right, soft, more less soft and things like that. Okay. You can achieve this in many different combinations, and to understand this I will give you the analogy of the domino. Okay. So, you would have played domino. So, in this case, for example, you just need to push one side. So, if you push one side, then whatever is at the other end is going to fall down. Okay. So, something similar concept that we are going to use. Actually, there is even a better domino video. I do not know if you have watched in YouTube, right? There is one domino video explanation. Let me see, maybe after the lunch break I may play that video. So, what happens is that you have a small domino and you have another domino, like that. Okay. So, if you make this domino fall, they will eventually make even larger domino fall. Okay. So, in the case of incoherent switching, what we do is exactly something similar. So, we have a soft layer and a less soft layer and a hard layer and a harder layer. Okay. So, by making the soft layer magnetization switches, if you apply a reasonably, let us say this layer switch is at 6 kilovolt, you produce say 15 kilovolt, of course, this will switch, right. So, you cascade this magnetization switching all the way down to the layer with the highest anisotropy. So, by making the soft layer switch, we make the magnetization switching all the way to the hard layer. Okay. So, as there are many approaches, it is called segmented perpendicular anisotropy. So, here you have soft, medium, hard. It's like having one layer with a 6 kilovolt, another layer with 8 kilovolt HK, and another layer with a 10 kilovolt HK, something like that. So, when you apply magnetic field, you can see the reversal happening. So, initially all the spins are pointed up red color, then when you apply some magnetic field, the softer layer reverses first, okay, you see blue color. So, the switching propagates from top to bottom, finally the whole stack is reversing. Okay. So, these are concepts that people use to improve the writability. So, instead of having only one magnetic rail which switches by Stoner-Wohlfarth, which will need more magnetic field, you break them into many layers. So, you also have some spacer in between, because you want to control the exchange coupling between the two layers. Okay. Imagine we have domino, right. Domino, we have some space. Suppose I stack all the dominoes next to each other. Then I cannot make the big domino fall. I need the space. Only then this will fall onto this, then cause momentum transfer and so on. Okay. So, you need some proper spacing. If there is no spacing, then all the layers are coupled, then that is like dominoes sticking to each other. You cannot make the dominoes fall. Okay. So, you also need certain spacer layer thickness, which will control the exchange coupling. Okay. So, now we see instead of one magnetic layer, now we see at least 5 layers. Okay. So, this is how the number of layers has become 20, something like that. Okay. So, let us do some questions again. Okay. 2 reduced to 1, very good. Okay. So, here we are using all these combinations to achieve lower transition noise, correct. Okay. Next one. Okay, so we use ruthenium layer for reducing DC noise as well as reducing transmission noise. I told you that there are two ruthenium layers, right? Low pressure ruthenium, high pressure ruthenium. Low pressure gives rise to better C axis texture. High pressure ruthenium gives rise to the grain segregation. So, this helps in reducing DC noise, this helps in reducing transmission noise. So, both should be ticked. So, all of the above is the correct answer. Okay, very good. You can all give a round of applause. Okay, this one I didn't teach. So, we also have a capping layer on top of all the magnetic layers for some purpose, but we will not go through that detail. Okay, so I told you that we have many layers in perpendicular recording media and they have some purpose. So, we learned that there is an addition layer, then the soft underlayer is not one layer, but it has 3 layers. So, that is for reducing the soft underlayer noise. Basically, these layers are for improving the writing performance. Then we have this layer for improving C axis structure of ruthenium. Then we have this layer of ruthenium for improving C axis structure of the recording layer, and we have this layer for isolating the grains, reducing transmission noise. And we learned that there are many recording layers. Okay, it is not one layer, many layers. And we have one recording layer on top to minimize some switching field distribution, which we did not discuss. Then on top we have at least 2 layers of carbon, which we will learn tomorrow or sometime. Okay, so this is how the layering of perpendicular recording looks like. You want to break early or you want to spend until 1? Another 5 minutes, yes. How many of you want to break now? How many of you want to stay? Okay, we will break now. Okay.